Welcome to the first class on an embedded processor. This is going to be a little bit overview about the class and how to learn, as well as how the processor resets and basic processor operation. So a little bit of an overview here on the agenda. Here we are talking about while we're going to use PowerPoint, some of our learning expectations. We're going to go through how the processor works, the ATSAM X51 memory map, a little overview about assembly instructions for the ARM, and we're going to go into file types and tools that are used to program embedded devices. So why PowerPoint? So PowerPoint generally sucks as a way to convey information, but it's great for being able to have talking points and show graphs and information. This is not meant to be a study guide as much as it used to highlight the topics. If you, of course, have any questions, please contact me, leave comments below. So one of the things that often is frustrating as you start to learn stuff is that learning takes time and practice. And as we start to learn, we can get frustrated because we don't feel we're learning fast enough or we're gaining confidence quick enough. So I'd like to go through some information about what it takes to become an expert in a subject. So first of all, let's talk about the Dunning-Kruger effect. The Dunning-Kruger effect is that as you start to learn something with time on the x-axis here, and you have confidence on the y-axis, as you start to learn, you learn really quick. You get a lot of information, and you think, man, I am an expert, and I'm highly confident I can get this to work. This is often called the Mount or peak of Mount Stupid. As you gain more experience and wisdom, you realize how much you don't know, and this is the valley of despair. Then slowly, as you gain more experience, you rise up in your confidence and you're on the slope of enlightenment. And if you think about a person at each step along this process, what might they say about how confident they are in their ability or how good they are at the subject? For example, at the peak of Mount Stupid, somebody might say, look at all these stupid people around me. I already know all this stuff. I can't believe they've been doing this for years and don't know as much as I know. Then in the valley of despair, it's like, wait, maybe I don't know it all. And then on the slope of enlightenment, how does anything work? You might be saying, is it too late to change my career? Okay, so an example of the Dunning-Kruger effect is a friend of mine was working with ARM processor cores. And I was talking with him about ARM's barrier instructions. And he told me there are 30 people in this world that truly understand ARM's barrier instruction. He says 15 works on the same floor I work on. And he goes, there's 15 people on that floor that understand the ARM barrier instructions because I pay 40 people to understand them. That is, knowledge and experience takes time. And just because you're paying 40 people to understand something doesn't mean they do. So it takes experience. Now, as you look at this, where is the danger zone? So if you look at this, the most danger is done in anything when you think you know something, but you truly don't. That is, when you're at the peak of Mount Stupid, it's when you have confidence that you know something, but it's not really true confidence. That is, you think you know more than you know. Less risky is when you're down here at the valley of despair and going up the slope of enlightenment. That is when you're on the working edge of that knowledge. Now, it's often said that it takes 10,000 hours to really know something. 10,000 hours is 40 hours a week for 5 years. Now, keep in mind, this 10,000 hours requires practice and gaining experience and working towards stuff that is more challenging. And so, to give you an example, you've probably been behind somebody driving, an older person, and they're driving really bad, but they have well over 10,000 hours of driving. But that driving has not been done with deliberate practice where they're continually improving their skills. That is, if you keep doing the same things you've always done, you're not going to get any better at it. So you have to have deliberate practice to improve. Let's get back now to processors, and let's discuss the ARM Cortex-M series processors and what it needs to know to start running. So at reset, the processor needs to know where to start running code and where to put the stack. The stack is a section of memory, and the processor needs to know the stack because the ARM Cortex-M series, that first instruction could be an invalid instruction. And when it gets an invalid instruction, it causes an exception or an interrupt. For interrupts to happen, the stack must be valid. So the stack has to get set first, and then the program counter, and then you can run the code. Now, to understand the stack and the program counter, it's good to have a basic idea of what processor registers are. Basically, the registers are a set of memory that is really, really fast SRAM memory. These SRAMs can be written at as fast as the processor core runs. They're typically on the Cortex-M series, they're 32-bit wide registers. And you see here we have 16 registers. You will notice that the bottom three are used for special purpose. Specifically, R15 is a program counter, and R13 is a stack pointer. The Cortex-M series also has a notation of two different stack pointers, the PSP and the MSP. We will discuss these when we get into RTOSes, but for right now, all we just need to do is view it as one stack pointer. These registers are often called the register file. These are not a file like a file on your hard drive, but more like a file folder, so a group or collection of like items. So that's why it's called a file. The program counter, R15, keeps track of the next instruction to execute. It's a bit complicated, but there is a YouTube video here you can watch to see it in action. Basically, the program counter, the processor grabs the instruction from the program counter, executes the instruction, increments the program counter, and then repeats. So the stack pointer. The stack is a section of SRAM, and a stack is typically a analogy to a stack of plates. That is, you can push a plate or put a plate on top, or you can take one off, pop it off the top of the stack, but you cannot get the data in the middle of the stack. This is not actually true the way the stack is implemented, but this is the analogy that has been used since the 70s. So here's an example of the way the stack works. You can push something to the top and it moves the top up, and then you can pop it off. The stack is a key part of the C programming language, and so it is needed to be able to run C on a processor. Now, to give you an idea of how the stack works, let's go through examples. So initially, the stack pointer is at 1000C. On the Cortex-M series, the stack increments down. So we go in here and we push like 0x0e onto the stack. This gets pushed at this address, 1000C, where the stack pointer is pointing. And then the stack pointer decrements to hex 1008. And so the stack pointer goes down from a high address to a lower address. So why do we have a stack pointer? Again, it's part of the C programming language, was based on the use of a stack. This is one of the reasons early PIC microprocessors really sucked, because they had no concept of a stack, so you could not really use C to program it. A stack is often used with function calls in C. So, for example, you have your main function and it calls another function. When it calls that other function, the main variables and stuff will often be pushed on the stack, or the registers will be pushed on the stack, so the other function can use those registers in the register file to execute that instructions. And when it returns back to main, it'll pop the previous registers from the stack and start executing the main function again. And again, since the interrupt may be called right after reset, the processor core needs the stack before we can start running. We will see a demo of that a little bit later. Now let's discuss the ATSAM X51 memory map. Here you will notice there is an embedded flash. The flash memory is non-volatile memory. It saves whatever's in it when the power's off. When you power it back on, it can read that memory and it's the same value. SRAM, on the other hand, is faster memory, but it is volatile. So when you power it off and power it back on, the SRAM changes. As you will notice, different processors in this family have different amount of SRAM and flash. This allows you to pick a processor based upon your application and how much code you need to run and how much SRAM you need to run that code. Additionally, you will note that the peripherals are memory mapped. We have a backup SRAM that's 8 bytes. This is backed up with a battery input if you hook it up to your processor. We also have non-volatile memory user row. Microchip uses this to store calibration data like the ADC and DAC calibration, as well as a processor serial number into memory. This is a flash memory. You can also, there's leftover memory in this user row that you can use for your application if need be. Now let's talk about the vector table. Vector table or exception table or interrupt vector table. They all mean the same thing. And basically, it's a list of addresses that is used to when an exception or interrupt occurs as to what function to call. The interesting thing with the vector table is you notice it starts at a low address and grows up. And the first entry is the initial stack pointer. Address 4, 32 bits later, is the reset vector location. This is the address of the first piece of code that should run when you start the processor. So these two interrupt values, or two vector table values, are critical to starting up the processor. You will also notice that there are some not hard fault and non-maskable interrupts here. And then at address 0 is RRQ0. So these first 15, or 14 if you will, 15, 14, interrupts are core interrupts. These are part of every ARM Cortex processor. As you go up above 0 for the IRQ number, these are part of the vendor-specific processor. So different processors, STM, Atmel, Microchip, will all have a different number of interrupts, but they will also always have these first 14 if they're an ARM core. Now, the ATSAM X51 has an additional 136 exception vectors. These are, of course, mainly used for peripheral inputs, and there are a lot of them. Typically, this exception table is stored at address 0 in flash. The Cortex M0 does not allow changing where you store this exception vector table. However, the Cortex M0 Plus, M3, M4, M7, etc. does allow changing where the vector table is stored in flash memory through the vector table offset register. I should mention also that this could also be stored in SRAM. The vector table offset register is just an address. One of the reasons the Cortex, these higher later Cortex cores allow changing the vector table offset register is to implement bootloaders. So your bootloader starts and it will use address 0, and then when the bootloader is finished, it'll change the vector table offset register to the interrupt vector table used for your application, and then start running your application. So the vector table offset register is great for doing bootloaders. This is one of the reasons I recommend that you only look at Core M0 pluses and above, especially if you need a bootloader. Okay, so when the processor resets, the first thing it does is load the stack pointer from address 0. Next, it loads the program counter from address 4. Then it starts fetching instructions from the program counter, executes the instructions, increment program counter, and then it repeats. Fetches instructions, execute. That's pretty much it. That's all the processor does. Fetches instructions, executes, increments program counter. Very simple. Now, one thing I'd like to mention is ARM has two types of instructions. There's ARM instructions and thumb instructions. ARM instructions are 32-bit instructions. Thumb instructions are 16 bits. I have read different data, but it appears that the Cortex M4 can run a mixture of both. Typically, I have also read that it only runs thumb instructions. Typically, we do only use thumb instructions for the Cortex M4, as that with 16-bit instructions, as you read flash memory, you might read 32 bits, but it gives you 2 instructions. So the flash memory can be slower, and you can still run at full speed. Now let's discuss different file types. So when you compile code for a processor, you have an output file type that you use. These file types, you can select different types of outputs you want to use. A very common one is called Intel hex format. These ends with the .hex extension, and typically is used for production programming of processors. The key thing to the Intel hex is that it is a text file, and it has a structure. It has a start colon here, byte count, address, record type, data, and a checksum. So this address is often key for programming, because on the Cortex M, the start address is 0, but for example, if your application has a bootloader, the bootloader might be at address 0, but your application might be at a higher order address. So knowing what address the bytes should go in is very important, and so the hex format includes that information. Another file format is binary files, and this is a smaller file. It has no CRC or address information. It's basically just the raw binary data that will be loaded on the processor. So if your code, for example, starts at address 0, the binary data and hex file are almost equivalent. However, if your code starts at address 1000, for example, the binary data has no way of knowing where that starts. So the binary data could start at address 1000. It could have all zeros for the first 1000 bytes, or it could be different. So binary files are still used, but I would recommend using hex files instead. Another common file format is the Motorola S-Record format. This is not used very much anymore, but you will see it occasionally used still. Part of the GCC compiler is Object Copy. This is a utility that will translate between different file formats. There are almost endless options, as you can see to the right on the command line options. We will see how this is used later on as we convert file formats to programming files, F files, and so forth. We also use this quite often along with S-Record Copy to add bootloaders to our program. Now let's discuss programming. So JFlash Lite is a program that's part of Seger's tools that you can use to program your board. The Segur J-Link is a very good tool, which I recommend everyone get because Segur has really nice tools. They are expensive. You can get Chinese knockoffs, but I highly recommend you support Segur and get their tools. The J-Link allows you to connect to the microprocessor and program code on it as well as debug code. The J-Flash Lite is again just an application that makes programming the processor easy, and it accepts most file formats like hex, binary, sRecord, etc. Now we're going to go and we're going to look at an example of how to program a board, get it up and running, and blink an LED. This is going to show us how to do the reset vector, stack pointer, etc. We will go into disassembly of the code, looking at the code, looking at the stack pointer, etc. Okay, in the links below you will see a link to the GitHub repository for this project. This project is designed to be ran with Visual Studio Code. If you're not familiar with Visual Studio Code, it is a very popular IDE that is getting more and more traction as time goes on. And so I will explain a little bit how to get everything set up, include the tools and so forth. So let's just get started. So the first step is you need to go to the GitHub repository, clone the project into a directory on your PC without spaces. Step number 2 is you need to install the XPack tools. There's a link here in the README of how to install it and the prerequisites. Once the XPack tools are installed, all you have to do is go into the terminal here after you open the project in VS Code and just type xpm install. This will run a script and it will install all the development tools used for this project into the XPacks directory here. So specifically what's going to be installed in here is the ARM GCC compiler for the Cortex M series. If we look here in the content in the bin directory, we will have executables, including the GCC compiler itself, object copy as we mentioned before, object dump, etc. We will also see in here there is a directory for the Windows build tools. This is a set of tools used to build code. It includes BusyBox, CP, which is copy, echo, the make tool, make directory, remove directory, and the shell tool. These are ports from Linux to Windows for the common build tools. You will also notice this project, there is a VS Code directory. This has settings in here for various things. So the CCP properties goes in here and is a setup for the C tools and CCP tools for VS Code. And so it needs to have a link to where our compiler is, which is in our XPack directory here. It needs to know that we're using GCC ARM so that the which CPP standard and compiler, so that as we program and have problems, it can automatically parse the problems for you. And then we are telling it we're using the Microsoft Makefile tools to build the project. There is some extensions here. These are extensions or plugins for VS Code that we will use. This includes GitLens, the Cortex debug tool, Makefile tools, and the CPP tools or C tools. The CPP tools allow autocomplete and IntelliSense for the C. We also have a launch tool. This launch tool will actually launch the debugger. You will need to change some of the stuff in here. For example, I am using a J-Link, Segur J-Link tool, and I have to give it a path to where the Segur J-Link GDB server command line version exists. And so this path may need to be changed for your computer. There is also the sentence here. And here we include the path to XPaths again for our makefile tool, our make tool. Then we have the task directory. This is set up with, again, make, path to make, and our build tools. This allows us to build the project directly from VS Code easily. Okay, the way the code is built is through a makefile. We will have a video coming up on how makefiles work, but for right now, the makefile should be set up so that you can build this project very easily. Once all your extensions are installed, you will see over here, these are a list of icons for the extension. You will see the makefile tool. You need to set the build target here, and so you can do that by clicking on this button and set it to the debug release. Then you can click this button to build the project. And you see here, it says nothing to be done because it's already been built before. We can also build the code here by hitting Control B, and it will go through and do the same thing as if we click this button. Next, we're going to load this code onto the processor. To do this, we're going to use this Cortex Debug Run and Debug tool. As you can see here, it says Cortex Debug. So we click on this to start the debugger. It's going to first try to build the code, then it's connect. Now it's loaded the code on the processor. It automatically stopped here at main on the code. We want to understand what's happening before we get to main. So we can go in here and we can look into our code, and in the startup directory there is Cortex handlers. And as you remember, we had discussed the interrupt vector table. And here is the interrupt vector table. And you see here the first thing we said was address 0 was the top of the stack. And then the next one was the reset handler. The reset handler is actually a function. So we want to stop at this function. So let's put a breakpoint right here. And we're going to restart our code. Now, as we restart our code, one of the things to notice is that we are actually running this code on the processor itself. And so let me see if I can switch over to that view for you. So here is our processor hooked up. Our J-Link's up here on the left. We're hooked up to our 10-pin Cortex debugger. We powered up. And now we're stopped at this point in our code. Now, we will go in here and let's see if we can see. Yep. I am looking for the peripherals for the processor. Sometimes it's hard to find where they put things. Okay. Here's our register. Remember we talked about our register files, R0. If we look at our program counter has a value 1B14, which is the reset handler plus 4. Remember, we load the instruction, then we increment the program counter. So this is the next instruction to execute. Now we can go in here and we should be able to see view disassembly somewhere. Again, it can be hard to figure out on, depending upon your IDE, where they store various things. So we want to find out where the disassembly view is. So let's see if we can go here and say disassembly. So Where in the heck is the disassembly view? Okay. Hang on a second. File open. In the context window of an emulator. So here we go. Here's how you open the disassembly view. You can right click on the file and click disassembly view. Now we have our disassembly. And you see here our program counter 1B14 is actually the address we're on here. You will also notice that we have our stack pointer is pointing at OX2000 to FF0. This is near the top of the SRAM for our processor. And so our memory map of our processor, if we go back here and look at our linker file, and we will go into the linker file in more detail, but the linker file tells us about the memory map. And we see that our RAM here starts at hex 2000 and ends at 3000. So 2FFFF is near the end of the SRAM. And that's where our stack pointer is. And so now, this is the first set of code that is going to be executed on the processor. That is, we have just reset, and this is the first line of code that starts executing. And so we can step through the code. This first part, we're going to fill the stack with a known value of dead beef. This is so the code can actually track the amount of stack we've used. We'll discuss this later. Then we're going to initialize the data sections. These are, best way to look at this is when you have a initial value set for a global variable, it needs to be initialized from flash that global variable has been initialized to the value. That's what this section here does. This clears out the BSS section, which we'll talk about later. We'll enable the floating point. We do the system init, which configures all the clocks and the processor speeds, and then we call main. And so now as we look here in our code as we start to run, we will actually go back here to main. And this is typically where most people start programming, is at the main section of code. And so let's run to this section by clicking the continue button. And you see we get to main. Now we can start stepping over the code. This and this, the sys-tick timers. This sets up a debug UART. We're going to log that we powered up. We're going to configure the red LED. And then we're going to turn the LEDs on. So if you look over here in the bottom right window where the processor is, if we step through this, we should see the LEDs light up. Now we're going to delay for 500 milliseconds and toggle the LEDs. And so we can just continue to run and we can watch our LEDs toggle. At this point, we have our code set up and we're debugging it. So congratulations. This is the end of our first video. Our next video, we will start discussing more about the processor and how other things work within it. Thank you for your time.